knows a lot about the science stuff. Professor Dave explains.
We just looked at three important five-membered heteroaromatic systems, those being furan, thiophene, and pyrrole. So let's take a look at one with six. Pyridine is the most relevant of this category, which looks essentially like benzene, but with one of the carbon atoms replaced with nitrogen. Pyridine is aromatic, of course, and is almost as aromatic as benzene, the only discrepancy being that the nitrogen withdraws a bit of electron density and reduces the symmetry of delocalization, reducing the resonance energy from 36 kcal per mole down to 28. But the electronic structure is the same, with the atoms in the ring all being sp2 hybridized, leaving an unhybridized p orbital on each atom to delocalize the pi electron cloud. The nitrogen has a lone pair, and this sits in an sp2 orbital. Unlike pyrrole, this lone pair does not delocalize, as it is not required to participate in resonance in order for the molecule to be aromatic. The 6 pi electrons from the 3 pi bonds are sufficient, so this lone pair is actually localized on the nitrogen atom. For this reason, pyridine is much more basic than pyrrole, as the lone pair is available to act as a proton acceptor, though not as basic as a regular amine, given that sp2 orbitals have more s character than sp3 orbitals, meaning they are held a little closer to the nucleus. In addition to acid-base chemistry, pyridine reacts similarly to other amines as an N-based nucleophile. It can undergo alkylation with an alkyl halide, or acylation with an acyl chloride, yielding a highly reactive N-acetyl-pyridinium salt. Oxidation with peroxy acids is also possible, yielding a stable pyridine oxide. Now, as an aromatic system, we might expect pyridine to undergo electrophilic aromatic substitution, like benzene derivatives and electron-rich heteroaromatic systems, such as those in the previous tutorial. However, this is not the case due to the N effect. Whichever Lewis acid would catalyze the relevant substitution, the nitrogen on pyridine will coordinate to it, being nucleophilic. And this renders electrophilic attack highly unlikely, given that it would result in yet a second formal positive charge, such as here, if Friedel-Crafts acylation were to occur, so this is not a likely process for pyridine. However, nucleophilic aromatic substitution is feasible, given nitrogen's greater ability to stabilize negative charges over carbon. This can therefore occur without any kind of activation needed, such as with the reaction below. The mechanism for this type of reaction was discussed in another tutorial, but to review, in this case, piperidine attacks the electron-deficient carbon bound to chlorine, which pushes a negative charge onto nitrogen. This can then come back up to kick off the chloride ion, generating the following product. In terms of pyridine synthesis, the most widely used method is the Hantzsch synthesis, developed by German chemist Arthur Rudolf Hantzsch in 1881. This has 4 components: 2 beta-keto esters, formaldehyde, and ammonium acetate. Under aqueous conditions, this yields a dihydropyridine, which is then readily oxidized to produce the aromatic system. A variety of esters can be used to produce non-symmetrical pyridines as well. Unlike the 5-membered heterocycles we've examined, with 6-membered rings, replacing nitrogen with oxygen or sulfur does not result in a stable neutral species, so these will not be discussed. However, there are stable derivatives of pyridine that have 2 nitrogen atoms instead of 1. There are 3 such structurally isomeric structures. If the 2 nitrogens are adjacent, we get pyridazine. If 2 apart, it's pyrimidine, and on opposite sides, it's pyrazine. These are all weaker bases than pyridine, although they share similar reactivities. Heterocycles of this variety are omnipresent in natural products, so it is clear that nature has devised an efficient route towards producing these biological subunits. For example, we need look no further than the nitrogenous bases in DNA, such as adenine. There is pyridoxine, also known as vitamin B6. Most of us have heard of nicotine, the addictive component of tobacco. And then there is quinine, an anti-malarial drug that was the focus of one of the tutorials in our study of the history of drugs. And with that, we have a preliminary understanding of some important heterocycles. Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.